These are the first half of the notes for the chapter 8 for APC. So in this particular chapter now we're going to talk about circular motion, so moving in a circle. So motion in a circle, again, velocity can be calculated distance over time, but when you're moving in a circle, the distance is 2 pi r, and the time to go around once around the circle is what we call a period. Since it's a specific time, we use a capital T symbol for that, as shown right here. But it's just the time it takes for objects to complete one rotation. And so we get that the velocity of an object moving in a circle is just 2 pi r over big T. Again, it just starts from here. It's just tailoring it to the fact that we have a circle. And objects don't like to move in a circle. They will go in a straight line if they can. So here's a question. A ball on a string is swung in a vertical circle. The string happens to break when it's parallel to the ground and moving up. So the ball is moving this way. What trajectory does the ball follow? The only thing keeping it moving in a circle is the string, and so it will go straight. So C is the correct answer here. So when we're moving in a circle, even if we keep a constant speed of, for example, 5 meters per second or 20 meters per second, when you're moving in a circle, your direction is always changing, and therefore you are accelerating. And we call that centripetal acceleration. The symbol is A with a little c. And it just means center seeking, because in order for an object to move in a circle, it has to get pushed toward the center of that circle. And so it's caused by just the changing direction of an object moving in a circle, and here is the equation for that. I believe this is on your formula sheet, v squared over r for centripetal acceleration. It is an acceleration, so it has the same units that we've been using for acceleration before. So, knowing we've got v squared over r, a fighter pilot makes a turn and pulls 8g. This just means that it's 8 times gravity. So it's 8 times stronger than gravity. If a pilot makes a second turn at the same speed but with a larger radius, then do you know about the centripetal acceleration? So if we think about, go with pen here, v squared over r, and we play the what if game here. So if we have the same speed, so we're not changing this, so we just keep that as a 1, but we're making a bigger radius, then we're going to have a smaller acceleration because we've got a bigger number in the denominator. And so we'd have c less than g. Okay, and if the radius of the second turn is twice as large, specifically, so that means that we're essentially going to cut that acceleration in half, then we'd get 4 g's. So he makes the turn and pulls 8g. If he wants to make a second 8g turn while going faster, going faster is going to make his acceleration bigger, but I want the same, so the radius is going to have to be smaller. And now we're saying, okay, if he's going twice as fast for the second turn, now here's where again, v squared over r. So we have to think about, we're going twice as fast. So v is basically 2. 2 squared is 4. And so the radius has to be 4 times bigger in order to make the same acceleration. And so if we start off with 5 kilometers, we need 4 times that. And so we're going to need 20 kilometers. Okay, and wherever there's an acceleration, there is a force. So F sub c, it's the force that causes that acceleration. And so we have, again, our just F equals ma, but then when a equals v squared over r, we can substitute that in. It is a force, so it is measured in newtons. It points to the center of the circle, just like the acceleration does. But it's kind of interesting because the centripetal force is not a separate, unique force. We don't ever identify a force touching an object that is F sub c, because it doesn't technically exist. It's actually some other force, friction, tension in a string, that causes the object to stay moving in a circle. And so, like I said, we don't really identify F sub c as a force. It's more of a category. It's a general, whatever force keeps moving in a circle. So for uniform circular motion, the net force always has to point to the center of the circle. And then you probably have heard this term before. Centrifugal or centrifugal force is used a lot in the popular media, but it doesn't exist. It's not a real force. It is used to describe the feeling of being thrown or pushed outward as you move in a circle. Because as you move in a circle, that's how you feel like you're getting thrown out to the outside. But we said that centripetal force pushes toward the center. This feeling of being thrown or pushed outwards is just inertia. It's just Newton's first law. Your body does not want to go in a circle. It's trying to go straight. It's trying to stay exactly what it was doing. And it's the centripetal force pushing you toward the center that keeps you moving in that circle. So we have an example here. I believe this is the last slide of doing these calculations. So you have a 2,500 kilogram car traveling at 40 meters per second around a curve of 50 meters. The car's centripetal acceleration, so if I do v squared over r equals a. So I'm going to have 40 squared over 50 equals 32 meters per second squared. So there's the acceleration. The centripetal force is just MAC. So 2,500 times 32 gives me 80,000 newtons. So that's how much force I need to stay in the circle going that fast. And then the question here, what is causing the centripetal force? The only thing that can be causing it right at the moment is friction. It's friction, and I better have that much friction, because if I don't have that much friction, I'm not staying in that. I'm not continuing to move in a circle. I will go in a straight line. And that is the end of the Chapter 8 notes.